Hello and welcome to RLab 5. This week we're going to look at the z-test. So let's go ahead and start with the one proportion test. This is the test you want to use if you want to see if a proportion is equal to some specified value, which you call the null value. And recall the null hypothesis is generally that the proportion is equal to some value. The alternative is the proportion not equal to some value. So p equal to p naught or p not equal to p naught. The next stage then would be collect the sample data, and for the most part this will be done for you, so we're just going to skip over that part. After that we'll check the conditions, and when it comes to this test there are two main conditions. One is that we have at least 10 successes and 10 failures. That's to kind of guarantee our sample is large enough. And the other one is independence between observations, which we'll assume that we have independence if we have random selection and or random assignment. From there, the point estimate will come from the sample data. It's going to be the number of successes divided by the sample size. From there, we compute the standard error, which for this test is generally the square root of p times 1 minus p over n, where p is the probability of success. Once we have those, we can compute the test statistic, which is the point estimate minus the null value divided by the standard error. And once we have that, we can find the p-value. With our calculators, we would use the normal CDF command, where you can take the absolute value of that test statistic to 999.01 and then times 2. If the p-value is more than 0.05, then we would fail to reject the null hypothesis, and that there's not enough evidence to go with the alternative. If the p-value is less than 0.05, we would reject. And we would reject because there's enough evidence to say that the results the null hypothesis is not likely to be true. Now we can do all that in R if we just know the number of successes, the sample size, what we use for the point estimate, and we know the null value. There's this command in R called the prop.test command. And the way it works is you just type in prop.test, and in parentheses we'd have x equal to the number of successes in our sample. We have n equal to the sample size. The p equal to whatever the null value is, so that's basically you're specifying the null hypothesis. The last part is optional. Technically, in order to get the best, get the answers that are most closest to our calculator, the ones we've been doing for the lessons, we'd add this correct equals false subcommand inside there. It's not strictly necessary, but the computations in R will more closely match the results from the normal CDF command in our calculator. Alright, so let's try this out. For this one, I'm going to use the abnormalities dataset. In the 1980s, it was generally believed that the congenital abnormalities affected about 5% of the nation's children. So right away, I'm going to notice that 5% would be the null value. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 randomly selected children and found that 46 of them showed signs of an abnormality. So I see, maybe success isn't the right word for this, but there are 46 abnormalities out of 384. So my point estimate would be 46 divided by 384. And you can see the data set itself is just the variable's abnormality, and then it was either yes or no, whether there was a presence of abnormality or not. Now, if you want to add the data set to R, there's this command, the read.csv command, that will add the ABN data set into R, so we'll be able to use it in R. So the data set has one categorical variable, abnormality, that records whether the child showed signs of an abnormality. So let's go over quickly the study design. This is a population, we're doing a study about children. The specific sample is the 384 randomly selected children. Now, this was an observational study. There's no experiment to randomly pick the children that have these abnormalities. This is an observational study. The specific variable interest here is that the proportion of children showing signs of an abnormality. We want to figure out what percent is the correct percent. As for the scope of inference, we can talk about population inference since the children in the sample were randomly selected. We can't claim causal inference. Again, this is an observational study. So children were not randomly assigned to treatment and control groups. As for the quantitative and graphical summaries, here I just go ahead and did the commands here. If you use the table, parentheses, ABN, you'll find there are 338 children that had no signs of an abnormality, 46 of them, yes. If you run the same command but you divide by the sample size, 384, you can get the proportions of each. So you can see that 88% of the children did not have abnormalities. The other 12% did. And if you want to create a bar plot, it'd be bar plot, parentheses, table, parentheses, ABN. You can see the bar plot over here. Nothing that fascinating about it. I mean, there's a lot more no's than yeses, which take it for what it's worth. As for the hypothesis test, we're trying to test whether the abnormality rate is 5% or not. And technically we want to see whether it's more than. We'll just stick with not equal to. Once we reject, then we'll worry about whether it's greater or less. And if we don't reject, then we don't worry about it at all. So anyway, our hypothesis is that the proportion is equal to 0.05. The alternative is the proportion is not equal to 0.05. The sample itself, there were 384 children, found signs of abnormalities in 46 of them, and there was no signs in the other 338. So the point estimate here in terms of the rate of abnormalities, 46 abnormalities divided by 384 children. The rate of abnormalities is about 0.12. So the point estimate is 12%. Now, as I said, go back here. 46 showed signs, 338 did not. That's at least 10 of each. So there are at least 10 successes and 10 failures. Again, in statistics, success just means what you're looking for has happened. Kind of odd saying 10 successes for abnormality, but let's just go with it. Anyway, we have 10 of each, and the sample size is certainly large enough. The children are randomly selected, so independence can also be assumed. The conditions for the one proportion z-test have been met. Now to use R, we'll set x equal to the number of abnormalities, 46, n equal to the 384, the sample size, and since we're testing 5%, I'll set the null value to 0.05. So the specific command would be prop.test, x equal to 46, n equals 384, p equals 0.05. And then, again, this last part is optional. I like to include it just so it gets closer to our actual calculator answers. Correct equals false. And this is the output. If I run the command prop.test, what you see below is the output from R. And you can see a lot of this we already knew. The data was 46 out of 384. The null probability, the null value is 0.05. The rest of it, we have, we're just about ready to talk about chi-square, but let's not assume it right now. Technically, R is using a chi-square test and not a z-test, but the results are pretty close, and this is a pretty simple command, so we'll go with that. Anyway, what is important is that part right there, the p-value. 3.494, e negative 10. If you're typing this into WAMAP, use a capital E, but basically they're saying the p-value is very small. When you see that e negative 10, that means the decimal should be moved 10 places to the left. So this is a very, very small number. This is definitely less than 0.05, so we should reject the null hypothesis. There's strong evidence that the rate of abnormalities is not 5%. And if you look farther down, you'll see the 95% confidence interval. And that appears to be around 0.09 to 0.16. So we are 95% confident that the true rate of abnormalities is somewhere between 9.1% and 15.6%. Now, since we wanted to test whether we wanted to compare it to 5%, we can see that these numbers are much larger. So the rate appears to be a lot larger than the claimed 5%. By the way, if you wanted to try a different confidence level, basically it's the same command, prop.test, x equals 46, n equals 384, p equals 0.05, correct equals false. Again, that part's optional. But if you add this little conf.level equal to, that allows you to change the confidence level. So in this case here, you can see I did this for 90%. So the 90% confident that the true rate of abnormalities is between 9.5% and 15%. And again, this rate appears to be a lot larger than the claimed 5%.